So it gives me a great pleasure to introduce Gianmarco Iodice. Gianmarco is a senior machine learning software engineer at ARM on the compute library team. He receives his master's degree from the University of Pisa in electronic engineering, and he has several years of experience researching and optimizing machine learning and computer vision algorithms. He's going to talk to us today and lead us in the exploration of a new class of Winograd algorithms to get even faster CNN. So please welcome Giancarlo.
So many thanks, Jose, for your introduction, and thank you very much to all of you for attending this presentation. I hope you are enjoying the Embedded Vision Summit. So my name is Gianmarco Iodice, and I'm a senior software engineer for the machine learning group at ARM. I joined ARM 4 years ago, and since the beginning, I have been working on enabling, deploying, and optimizing intelligent vision applications on ARM-based platforms. And today, I have a great pleasure to talk about an efficient and fast algorithm which can be used for accelerating our convolutional layers in our convolutional neural networks. The name of this algorithm is Winograd filtering algorithm. So let's start to see the agenda for today. After a very brief introduction about ARM, where I'm going to spend just a few words about the company I work for, I'm going to deep dive into the world of convolutional neural networks, presenting an overview of the current trends inside the convolutional neural networks used for object recognition tasks. After that, I'm going to spend one section talking about potential optimizations for convolutional layers when the convolutional layer is implemented with GEMM, so with a matrix multiplication. In this section, we are going to see what is the memory coalescing and also the important role of the local workgroup size, which plays a significant role, especially if we deploy a matrix multiplication on a GPU, especially on the embedded GPU. However, the main section of this talk will be about the Winograd filtering algorithm. And this part essentially will be the core part of this presentation. I'm going to present a mathematical background to understand how Winograd works, and also how to demonstrate the complexity reduction introduced by Winograd. We'll see the algorithm design, and in the end, the performance achieved on our platforms. So, as I said, I'd like to spend a few words about ARM. And ARM is a British multinational semiconductor IP and software design company owned by SoftBank for roughly 2 years. Sorry. And yes, with headquarters in Cambridge, United Kingdom. So if I could use 2 words to define ARM, I would definitely use innovation and growth. Innovation, because the technology designed by ARM are shaping the digital world, because are enabling most of the digital products available in the markets. Bear in mind that over 90% of our smartphones, for instance, are enabled by an ARM processor. Moreover, with the Project Trillium, we are going to enable as well machine learning applications and even intelligent applications at the edge. But ARM is also growth, because in 25 years, ARM was able to ship 125 billion devices powered by an ARM processors. Just in the last 4 years, ARM shipped roughly 50 billion devices, and we are expecting to doubling this number in the next 4 years. So it's for sure an exponential growth. So let's do the kickoff, and let's talk about convolutional neural network. And I like to start from where I finished last time, because 2 years ago, I was here at Embedded Vision Summit, and I talked about 2 approaches for implementing a convolution layer. One based on the fast Fourier transform, and one based on the matrix multiplication. The presentation essentially present the advantages and also the drawbacks of both implementations. And at the end, we discover that the fast Fourier transform approach is good, but it's only good for large kernel sizes and with stride equal to 1. And the stride, it means the distance between two consecutive kernel applications. What can we say now about our convolutional neural networks? So essentially, this table reports the essentially which kind of convolutional layers we can find in the recent CNNs. Essentially, the table reports for each row some networks which have been developed in the last 2 years. For instance, GoogleNet, Inception v3, Inception v4, MobileNet, ResNet 50, and VG16. And each column reports the percentage of a kind of convolution kernel size over the total amount of convolution kernels. So essentially, in the first column, we have the total amount of 1-by-1 kernels available in the network. The second column reports the number of 3-by-3 kernels. The third column, the number of 5-by-5 kernels. And in the end, we have the other columns, which are not 5-by-5, not 3-by-3, and not 1-by-1. So if we look at this table, the current trend is dominated by even smaller convolution kernels. So not just 3-by-3. For instance, VG16 is dominated by just 3-by-3 kernels, but also by 1-by-1. And a typical example is MobileNet, for instance. But if you pay attention to this table, you can notice also that for Inception v3 and Inception v4, we have a significant percentage of convolution kernels which are not 5-by-5, 3-by-3, or 1-by-1. But don't worry, because are small, because our 1D kernels are 3-by-1, 1-by-3, so are still small. So with this graph, I reported the layer breakdown for the previous networks. So essentially, I reported the percentage of the time spent for the three most computation expensive functions available in the networks. We have a convolution, batch normalization, and fully connected layer. And if we zoom in, we can see an interesting thing. So essentially, the fully connected layer is available only for few networks. And also, the time spent by fully connected layer is only considerable for VG16. So the question is, why we are not able to see fully connected layer in other networks? And also, why is negligible the time spent by the fully connected layer in GoogleNet and Inception v4? To understand this aspect, we need to understand how we are going to implement a fully connected layer. So, and this slide should describe this, because neurons in the fully connected layer have connection to all output of previous layers. So what does it mean? It means a vector by matrix multiplication. But this is a problem, because vector matrix multiplication is memory bound. If you can compare vector matrix multiplication to a matrix multiplication, essentially we can see that for the matrix multiplication, we have O and 3 operations over O and 2 data. And for vector matrix multiplication, we have O and 2 operations over the same amount of data. So essentially, we have a high ratio between the memory accesses and the arithmetic instructions for the vector matrix multiplication. And this is a problem, because we can't hide the memory latency when we fetch data from the memory. Moreover, when we think about the vector matrix multiplication, we have few data reuse, and we have limited temporal locality. So this is the reason why in recent networks, we are not able to find fully connected layers, or if we use it, we reduce the number of layers for fully connected. What did we do to improve the performance of GEMM-based approach? So GEMM-based convolution essentially has this pipeline, more or less. So, and in order to reduce the computation to matrix multiplication, we need to reshape our input tensor. which returns a 2D matrix, essentially. After that, we can compute the matrix multiplication. And at the end, sometimes, we need an extra function which reshapes the 2D output of GEMM to the correct shape of the output tensor. This implementation is good and is demonstrated by the graph below, essentially, because the graph below reports the time spent by GEMM, image to call, and call to image. And if we look at this graph, the time spent by image to call and call to image is negligible in almost all cases, except maybe the first convolution layer. So what did we do to improve the performance? One slide is not enough to explain all the possible optimizations for GEMM, of course, and this is not the talk about optimizations for GEMM, but I have reported 2 interesting things I work on in these 2 years at ARM. So one concerns the limited numerical precision, because essentially we can use, for instance, half floating point precision, or mixed precision with floating point and half floating point. But also we can use int8 operations as well. In this talk, I'd like to focus the attention on this thing, improving the GPU cache utilization. Because most of the time, implementing an implementation on the GPU, it requires to understand how to access correctly the elements in memory in order to improve the cache utilization. And the memory coalescing and the local group size tuning will play an important role. To understand this aspect, I need to introduce some OpenCL concept, because I'm not sure all of you are aware about OpenCL, but OpenCL is a framework for essentially deploying massively multi-threading implementations on a general purpose processor. This is more or less the architecture we should have in mind when we use OpenCL. So essentially, we have the global memory, which can be a dynamic RAM, the L2 cache, and we have the compute device. The compute device can be a GPU, can be a CPU, or can be an accelerator, for instance. Inside the compute device, we have several compute units. And each compute unit has an L1 cache. But let's summarize everything in a slide. So compute device can be a GPU, CPU, or accelerator, and is made up of several compute units. Each compute unit, for instance, can be a GPU core, CPU core, DSP, for instance, has its own L1 cache and can execute n threads in parallel. For the OpenCL point of view, essentially, the threads is called work item. Each thread executes the same piece of code, which is called OpenCL kernel, and the thread ID is used to access different memory locations. This is the key aspect we'll see later when we are going to talk about the local workgroup size tuning. Because essentially, the collection of threads running at the same time on a compute unit is called workgroup, okay? Local workgroup. And the number of threads inside the workgroup is configurable. So what we want to do for improving the cache utilization on the GPU? Essentially, we want to improve the cache utilization at L1 level, but also we want to improve the cache utilization at L2 level. So the idea is this. So threads of the same workgroup, which are running on the same compute unit, should access consecutive memory addresses. So this is memory coalescing. So the matrix multiplication is a good example for explaining this, because inside the dot box, we have 4 threads running on the same compute unit. And the 4 threads on the matrix P are going to access different columns. So on the matrix A, we are going to access the same row. On the matrix B, different columns. It might be a problem if we look at the matrix B, because we are going to read different rows every time. However, thread 0 is going to help thread 1, because when it's going to read elements from a memory, essentially the memory loaded will be available for the thread 1, which will help thread 2, which will help thread 3, and so on. This is the memory coalescing. So what about the L2 cache utilization? So we want to improve also the L2 cache utilization. And the idea is, yes, I want to reuse the same memory block between different compute units. And how can we explain this with the matrix multiplication? In this manner. So each dot box is a compute unit with 4 threads. In the matrix A, each compute unit is going to read different row. But on the matrix B, each compute unit is going to read the same memory block. Let's zoom in the matrix B. This is more or less the situation. So we have the same amount of threads for the compute unit, 4 and 4. And we are going to reuse the elements of the compute unit 0, for instance, in a compute unit 1. This looks trivial. This looks good, but it's not trivial at all. So essentially, for improving the L2 cache utilization, we need to play on the local workgroup, okay? Tweaking the number of work items in a workgroup can have a huge performance impact. However, setting this value is not trivial at all, because it depends on the cache size, it depends on the maximum number of threads per compute unit, it depends on the workgroup dispatching, and other things. So how can we solve this problem? In the ARM Compute Library, and if you are not aware, essentially, the ARM Compute Library, it is a free and open source software library developed by ARM for enabling intelligent vision applications on ARM-based platforms. We implement an LWS tuner to look for the optimal configuration to use, or the optimal local workgroup size to use, using a brute force approach. And what kind of speed up did we see using this? Huge. The uplift is very huge. I mean, for VG16, we achieved roughly twice better performance just changing this number. But the uplift is for all the networks, between 1.12 up to the 1.8 of VGG16. So let's move to the hot topic, the topic of this presentation, which concerns Winograd. But don't forget what we have learned with the previous section. So what is our goal? Reducing the number of multiplications, tackling direct convolution. So essentially now, let's forget the GEMM-based approach. So let's forget image to call, let's forget call to image, let's forget GEMM. What we want is to reduce the amount of multiplications of direct convolution. So direct convolution is simply the sliding window approach we used to see, for instance, in image processing. It's the same approach. Before exploring Winograd, let's focus this tiny matrix multiplication, because we'll see later on when I'm going to talk about the mathematical background we have behind Winograd. This is a 2 by 3 by 3 by 1. Okay, it's a matrix by vector operation, which returns a vector of 2 elements. How many multiplications do we need to perform this kind of matrix multiplication? Essentially, 6 multiplications and 4 additions. This is trivial. So with Winograd, we are going to reduce the amount of multiplications needed for this small matrix multiplication. And to explain this, I need to talk about how I need to introduce a 1D filtering, because essentially the first step to explain Winograd is essentially concerns the convolution layer with 1D signals. Okay, so let's take, for instance, a 3-tap filter, which is a 1D kernel with 3 elements. And if we want to compute one output element, we need just to do a dot product between the elements of the kernel and the elements covered by the kernel inside the input signal. So we have a vector by vector operation, which returns R0, for instance. So K0, K1, and K2. So what do we need to do if we want to perform the next output element? So we shift by one element the sliding window, and essentially we have an overlap between the previous window and the current one. On the left-hand side, we have exactly the same matrix multiplication we have seen before, okay? But it's not exactly the same because it has 6 entries, but it has only 4 input values, because when we compute 2 output elements using 1D kernels, essentially we have an overlap between the convolution operations, okay? So we need just 4 input values. In particular, K1 is available for both rows of matrix A, and K2 is available on both rows of matrix A. So Winograd, in 1980, found an algorithm to perform this operation with just 4 multiplications. And the name of this algorithm is Winograd minimal filtering. How does it look? It looks like that. So essentially, the output is still a vector, but it has only additions. I mean, it doesn't have just addition because we need to compute the M0 values in the output vector, which are here, essentially. So M0, M1, M2, M3 are the key elements needed for computing the 2 output values, okay? And we have 4 multiplications. However, if you pay the attention, especially for M1 and M2, we don't have only 1 multiplication. We have at least 3 multiplications for multiplying by 0.5 W0, W1, and W2. However, if we consider just the inference problem, the weights are constant. So this part can be pre-computed. And essentially, we have only 4 multiplications for performing our matrix, our tiny matrix multiply. However, for convolutional networks, we have 2D images, okay? What can we do to extend Winograd to the 2D case? We can simply nest the algorithm to form a minimal 2D algorithms, okay? So instead of having 4 input values, this time for computing a 3x3 filter, we need 16 input values to compute a 2x2 output. So on the left-hand side, I have reported the 16 input values. And on the right-hand side, I have reported the 2x2 output values that we are going to compute. So with the following slides, I'm going to explain what nest means, essentially. So on the right-hand side, we still have the input image and the filter transform. And on the right-hand side, I have reported essentially the matrix multiplications to perform the 2x2 values, okay? So let's analyze the matrix multiplication, which now is not anymore the 2x3 by 3 by 1, but is a 4 by 9 by 9 by 1. In this case, if we pay attention, we can split the matrices, or the matrix A, in submatrices. Each submatrix has the same structure we have seen before. So each submatrix has 6 entries, but just 4 input values. Moreover, we have the same submatrices for the 2 rows of our for essentially 2 rows of the matrix A. So essentially, the submatrix in position 1 by 2 is the same of the submatrix in position 2 by 1. But also, the submatrix in position 1 by 3 is the same of the submatrix in position 2 by 2. But this means that I can reduce this matrix multiplication in this manner. So we still have 4 input values, which are not anymore scalars, but are matrices. We have K0, K1, K2, and K3. And we know how to solve this problem, because we have seen that before. So now, instead of having 4 multiplications between scalars, now we have 4 multiplications between matrices. How many multiplications do we need to perform each matrix multiplication? Just 4, because we have seen before the submatrix has the structure that we have seen before talking about the 1D Winograd. So, since we have 4 matrix multiplications, and for each matrix multiplication we need 4 scalar multiplications, at the end we require 16 multiplications instead of 36 of direct convolution. And this means 2.25 multiplication complexity reduction. However, Winograd is great. We have seen the complexity reduction, but what do we really want? We want to reduce this operation to a matrix multiplication. And the reason is simple, because matrix multiplication is highly optimized for different architectures, especially on general purposes. We have very highly optimized versions on CPUs, GPUs, accelerators, FPGAs as well. And this formula will help us to reduce what we have seen with the slides before, to reduce Winograd to a matrix multiply. Let's analyze the formula. So the formula says you need an input transform, okay? But you need also to transform your weights, and this operation can be performed only once if your weights are constant. If you do these transformations, essentially, the core part of algorithm will be essentially just an element-wise multiplication, okay? However, to obtain the correct result, you need to transform once again using an output transform. Those are the main ingredients of Winograd if we use a matrix multiplication. And essentially, the algorithm looks like this. So we have the input, which passes through the input transform. We have the weights, which passes through the filter transform. We have the batch GEMM, which now is not anymore a single matrix multiplication. We are going to have more than 1 multiplications in parallel. In particular, for this case, we are going to have 16 GEMMs in parallel. And at the end, we need an output transform to obtain the correct result. So how the input transform look like? So essentially, for each 2x2 output tile, we need to take the corresponding 4x4 input tile in the input tensor, okay? Once we have the 4x4 input tile, we need to perform this operation with these constant values. So essentially, it is a tiny matrix multiplication, which returns a 4x4 output matrix. The 4x4 output matrix contains the 16 values, which must be stored across the 16 channels. What about the filter transform? It's the same. We have a similar behavior of the input transform, but instead of having a 4x4 input tile, we have a 3x3 input tile, okay? And we perform a similar operation with these tiny matrix multiplications. Just one thing, because of course, for computing these operations, the input transform and the filter transform, we need more memory. We increase the memory footprint, okay? Once we have the filter transform and the input transform, we are able to reduce the operations to a batch GEMM. So we can run in parallel these 16 GEMMs, okay? And we can move the computation to the final stage, which is the output transform. It is similar to the input transform and filter transform, but in this case, the values will not be any more on the same region, but will be across the channels. So essentially, we need to load the 16 values across the channels, and we need to perform a similar operation of input transform and filter transform. This operation will return a 2x2 matrix, which should be stored in the correct position of the output tensor. So what can we say about the memory footprint? Because Winograd is great, but what can we say about the memory footprint if we compare Winograd to the GEMM-based approach? So assuming a 3x3 kernels with unit paths and unit strides, we have this table should summarize or should compare the GEMM-based approach with Winograd. So the input transform is essentially similar to the image to call we have for GEMM, but the memory footprint is less than the image to call. Essentially, we have a reduction of 0.44. However, for the GEMM-based approach, we don't have any filter transformations, so we need to take into account this. And also, if we look at the output transform, this requires 4 times the memory needed by the call to image. So let's see the optimizations. Okay, let's talk about the optimizations for the input transform and the output transform, because if we consider just an inference problem, essentially we are not interested to optimize the filter transformations. We have seen that we have tiny matrix multiplications. So the idea for for optimizing the input transform and the output transform is to expand out the matrix multiplications. And the reason is simple, because if we expand out the matrix multiplications, we don't need any for loops, okay? Which is pretty important. We don't have any branches in our code. But also more important is this, so we can reuse partial results in different places of the code. So it's not, this part essentially will be much more clear with when we use Winograd for bigger output tile. But essentially, if you don't expand out the computation, the compiler most of the time can't do that for you because you're using floating point operations. So for instance, optimizations like factorization, unless you are enabling the fast math computation, the compiler doesn't introduce any optimization in order to preserve the order of the arithmetic operations. Okay? What about batch GEMM? Nothing. We don't need to do anything because GEMM is already optimized. So the same general optimizations for GEMM are still valid for the case of batch GEMM. On the GPU side, we can improve the performance performing the 16 GEMMs in parallel. So what does it mean? Essentially, we can dispatch a single job instead of dispatching 16 different jobs, okay? And this means reduction of the driver overhead. This means also reduction of the memory transfer at the same time and improvement of the GPU utilization. Why we improve the GPU utilization? It's simple because since we increase the GPU workloads, we have more threads, and with high probability, we can keep all the GPU cores busy at the same time. So let's analyze the performance, okay, of Winograd. But let's start analyzing the breakdown, okay? So this graph reports the time spent by the input transform, by GEMM, and by the output transform. And we can see an interesting thing. So this graph is for VG16. And the reason why I reported VG16 is because VG16 has only 3x3 kernels. So it's a good network to explain the overall benefit introduced by Winograd. So this graph shows this thing. Deeper we go, a negligible performance for the input transform and the output transform we have, okay? So for the first convolution layer, which is the first bar on the left-hand side, we can see that the output transformation is not negligible at all. Most of the time here, we are going to spend time just reshaping or just transforming our output values. So GEMM is not the heart of this convolution layer. But in all other cases, GEMM is essentially where we are going to spend most of the time, which is great. The performance for this slide concerns the CPU implementation. So what about the GPU implementation? we have more or less the same story here. So deeper we go, and negligible performance for input transform and output transform we have. The same behavior we have seen before for the first convolution layer, we can see here for the GPU implementation. So the output transform is not negligible for the first convolution layer, or better, when you have only few input channels. What about the speed up of these convolution layers? The theoretical is 2.25, and with this implementation on the CPU and the GPU, we are able to achieve roughly the theoretical maximum value, so essentially around 2.2 for some convolution layers. In some cases, we have 1.7, 1.6, but the overall benefit is great. I mean, we are over 1.5 times better performance in almost all cases. Just in one case, we could expect it, we are not faster with Winograd. And it is the first convolution layer when we have only 3 channels for the input tensor. So what about the overall speedups? Because I talk about VG16, which is a good example because it has only 3x3 kernels. But we have networks where the 3x3 kernels are, we have only not just 3x3 kernels, but we have also kernels of size 1x1, 5x5, or other kernels. And with Winograd, anyway, we are able to speed up also those networks. So the overall speed up is great, between 1.12 roughly to 1.8 of VGG16. So it's pretty good. But OK, so the algorithm presented used 2x2 output values. So what about having even bigger output tile? So instead of having a 2x2 output tile, what about having a 4x4 output tile? Yes, we can do that. And the complexity, the multiplication complexity reduction now is 4 times. In order to perform this operation, we can use the matrix transformations reported in this slide, for instance. Okay. So, and we have the input transform matrix, the filter transform matrix, and the output transform matrix. As you can notice, now we have bigger matrices to perform a bigger output tile. So we need to be careful when we increase the output tile because we reduce the number of multiplications, but also we increase the overhead for transforming the input and output tensors. So what about the performance of this implementation? So roughly, we have this similar behavior we have seen for the 2x2 case. So deeper we go, and negligible performance for the input transform and output transform we have, which is great. But what about the uplift of the performance? So the speed up, also in this case, is great. But we achieve not 4x better performance, but we achieve, I think the peak is around 3.4 or 3.5. But why we are not able to achieve the 4x expected? So the reason is simple, because as I said, the time spent by transforming the input and the output are not negligible at all. So this is the reason why we are not able to reach the 4x expected. So what about the speed up of our networks in general? As we have seen for the 2x2 case, also for the 4x4 case, we have an overall speed up, which is between the 1.10 and between 2.6 of VG16, where we could expect a better result because we have only 3x3 kernels. So far, so good in terms of performance, but what can we say about the accuracy of Winograd? So the accuracy has been evaluated in 2 different ways. One, using a mathematical approach, evaluating the absolute error, and one, evaluating the accuracy for our networks. So for what concerns the accuracy of the mathematical approach, essentially, we use a reference implementation with double precision. So we use a direct convolution with double precision, and we fill the tensors with random values between -1 and 1. We compare the reference implementation double precision with direct convolution in floating point, and Winograd 2x2 output tile, and Winograd 4x4 output tile. And this is what we have seen. So essentially, the Winograd 2x2 is more accurate than direct convolution in floating point. However, we have a drop of accuracy, or we have an increase of the error, increasing the output tile, for instance, with a 4x4. But what about the accuracy or the overall accuracy for our networks? So we performed the accuracy on the validation data of the ILC-VRC 2012, which is a challenge which is held every year to evaluate the state of the art in terms of image recognition for using neural networks. And we evaluated 50,000 images center cropped. We evaluated the accuracy on GoogleNet, VG16, and ResNet 50, and this is what we have seen. So the accuracy does not change with both Winograd 2x2 and Winograd 4x4 output tile, which is definitely great. So before closing the presentation, I'd like just to report some current investigations we are performing. First of all, we are trying to understand also the impact of larger output and kernel sizes. We have already implemented Winograd for 5x5 kernels, but also we are trying to understand the 6x6 case for kernel size with 3x3. And another interesting investigation concerns the limited numerical precision, because also we have presented a floating point implementation, but what about a limited numerical precision? And we are trying to understand if the mixed precision between half floating point and floating point can be used with Winograd. We are not totally sure about the in-state optimizations, because essentially for performing this Winograd, we need maybe in32 accumulators. So if we use in32 accumulators, maybe we don't see the benefit that we could expect. So here we go for the conclusion of this talk. And for sure, I can say that Winograd represents an incredible opportunity to improve further the performance of our convolutional neural networks. We have experimented, as we have seen with this presentation, over 2.5 times better performance on VG16 using Winograd with 4x4 output tile, and also without deteriorating the accuracy, which is pretty important. But the other important takeaway is this. So we have a new algorithm, but GEMM is still the heart of convolutional network. So this means that we don't need to spend the effort on optimizing the core part of Winograd, because we can use directly GEMM. However, we need to be careful, because we need to optimize the input transform and the output transform, which in some cases cannot be negligible. And in the end, also we have discovered that Winograd is a good implementation, not just for the GPU, but it's a great implementation also for the CPU and maybe also for accelerators. So before finishing, some references, because this work has been done, of course, following the fast algorithm for convolutional networks written by Andrew Levin and Scott Gray. And also, if you're interested to understand how Winograd works or some reference implementations, I suggest to have a look at the compute library, where we have this implementation available. And I think I've done for today. Yeah. Many thanks for your attention.
Thank you, Gianmarco, for a great talk.
Thank
you very much. And so there are 2 microphones in the halls. If you have questions, please line up. In the meantime, I have a question. So what are your goals for the next year? What's a the tough goal to achieve in the next year?
It's a super difficult question. So honestly, I like to spend time on trying to implement Winograd with mixed precision. So I think the next step will be to understand if we can use half floating
point and 8-bit.
Yeah, and 8-bit. I think this will be my next task for Winograd for sure.
And what is your sense? What do you expect?
So I expect that maybe the half floating point precision can play an interesting role, especially if we can mix the precision between floating point and half floating point. Unfortunately, I'm not totally sure about the int8, but I hope to use the int8 optimizations as well for Winograd.
Right, yeah, that's... Oh, here we have one question.
Yeah?
Please.
Actually, I have a question about the integer approach, about the accuracy. In the previous slides, you mentioned that integer 8 would probably require integer 32 accumulators. How about the multiplier side?
So yes, I mean, unfortunately, I think we need not just integer. What I want to say essentially, we need something bigger than 24 bits, I think, for Winograd. And the multiplications can be between 8 bits, maybe, but we are not totally sure. So essentially what we are trying to understand is this. So if the output of the filter transform or the input transform should be an integer or a char. This is the question we are not, I mean, we don't have the answer so far.
Can we compare like a TensorRT or those kind of integer 8 solutions? They also do 2 by 2?
Yes, it's something like that. I mean, so it's difficult so far to understand the accuracy because as we have seen also, we could have a drop of accuracy with Winograd because every time you change the order of your operations, essentially, you change also the result. So, and at this stage, essentially, I don't have the answer for the int8 because we are not totally sure if we're going to use int32 for the output of a filter transform or the input transform, which are going to GEMM, essentially.
That's great. Have you observed similar accuracy requirement in the FFT approach 2 years ago? You said that for large kernel sizes, you tried FFT, which is great, but do you see also similar accuracy requirement or precision? You need integer 16 or integer 8 is good?
Okay, so for the accuracy of the FFT, we didn't do any investigation, and the reason is simple, because essentially at the beginning, we tried to find the optimal way to optimize our convolution layers. And we found that GEMM-based approach is good enough, okay? So, and that was the reason why we didn't care at the time about the FFT, because most of our networks, especially for object recognition tasks, required only small kernels. And then all the efforts have been put to a GEMM-based approach. So we have evaluated just the accuracy using GEMM.
So last one. So you, in your accuracy plot, right, you found that the Winograd 4x4 got much higher loss of accuracy compared to Winograd 2x2. Is that a simple observation, or you try to figure out there's any reason behind it?
So Winograd,
do you expect larger, like a 6x6, would be even worse?
I mean, we expect bigger with 6x6. We need to consider this. So from the mathematical point of view, it's the same for Winograd. But the thing is, we changed completely the order of the operations, and we are using floating point. So essentially, changing completely the order, essentially, we have a different result for this reason. So it's not an actual error. It's an error because we compare something which performs the operations in a different way.
Right. And why the size matters in the accuracy?
Okay, this is an interesting question because essentially we are going to introduce the coefficients anyway used are integers, okay? And so using the integer coefficients, we are going to introduce anyway quantization errors with the floating point implementation. So bigger we have the output tile, and a bigger drop of accuracy we have, unfortunately.
Thank you.
Welcome.
Thank you. Any other Any other questions from the audience? So Winograd seems to work really well for VGG16.
Yes.
And then, but you did show a graph where it said that Inception didn't do as well, correct?
Yes.
Is that just because of the size of the kernels?
I mean, yes, Winograd works pretty well when you have, if you have Winograd 3x3, works pretty well when you have a lot of 3x3 kernels in your network.
Right.
If you have, for instance, a network with only one convolution layer with 3x3, we don't expect a huge uplift of the performance.
Right.
I think for Inception V3, we have a small uplift, but we still have it. But the overall benefit is essentially for all the networks. Just one network, we don't have the uplift, and is MobileNet. And the reason is simple, because we don't have any 3x3 kernels. So we have only 1x1 kernels. So this is the reason why I haven't reported the performance for MobileNet, because we couldn't compare that.
Any other questions? No? Okay, thank you, Gianmarco. Great talk. Thank you very much.